Hi everybody, welcome to my YouTube channel, Lit Art Sci. Lit is for literature, art is for art, and sci is for science. My name is Zainab Kordi. I have PhD in quantum optics and light-matter interaction. In this channel, I will talk about different scientific topics. In today's video, I would like to talk about entanglement, which I was working on in my master thesis and also in my PhD thesis. But why entanglement is important and how we could measure entanglement. Many of us are working with classical computers, which are based on classical information, binary information actually, 0 and 1s. But if we have the quantum computers, it's much more faster and it is much more secure. So many physicists and engineers were working together to make this dream come true, actually. So entanglement for the first time was presented in EPR paper in 1935 by Einstein and his students, Podolsky and Rosen. They presented, can quantum mechanical description as a complete description or not? Is quantum mechanics a complete theory or not? So entanglement was a bizarre and mysterious feature which didn't have any counterpart, classical counterpart, and it couldn't be justified based on classical physics. So if I want to talk about entanglement, entanglement can be occurred between different subsystems, like two atoms, two photons, an atom, and photon. You know, when we are talking about quantum, it's pretty different from classical physics. In classical physics, we are talking about macroscopic objects which are actually obey the Newton's law for describing about the motion, the force of the macroscopic objects. But when we are talking about quantum, we are talking about very small universe, very, very small scale, like the atom, electron, photon. And the law of physics are not obeying the Newton's law. And actually, we needed to use the quantum law for the quantum universe. So, and the measurement and the philosophy of the measurement actually is pretty different in quantum physics. We know that the first lesson of physics is measurement, and measurement is very, very important. And we have to say that measurement without measuring the uncertainty is meaningless. So we always have uncertainty in our measurement. So, and in quantum physics, actually, the measurement has different meaning. The sequence makes sense. It means that which measurement is done first and which measurement is done second. Okay, so we have to care about the permutation. And so basically, Einstein, Podolsky, and Rosen, they consider two subsystems which are correlated. It means that they are simultaneously know about each other. I will give you an example. You know about photon. Photon actually is a quantized part of the light. It's pack of the energy. It's quantized. It's not continuous. So just consider two photons which are entangled at the beginning because of the interaction. And these two photons are in the single state. If you put one photon on the Earth and the other photon on the moon, and if you measure the one property of this photon on the Earth, for example, if you measure the spin of this photon on the Earth, and the result of your measurement is spin up, and then if you measure, and without measurement, actually, you know the spin of the second photon on the moon should be down. And this kind of mysterious correlation, and it is simultaneously actually was called by Einstein spooky action at a distance. And that was pretty interesting, and it was very bizarre. So after that, Schrödinger actually was writing a letter to Einstein, and for the first time, Schrödinger named this quantum feature of the nature entanglement. So Einstein, Polsky, and Rosen were presenting a hidden variable to justify this full quantum property of the nature. They were thinking that maybe there are some variable in the nature that they are hidden from humans' eye. And then Bell actually was presenting a theory which was called Bell inequality. And Bell inequality was special formula to justify the determinism point of view of EPR paper, an EPR experiment. After that, many physicists were focusing on Bell inequality, and Bell inequality was violated by quantum. Even some experimental quantum physicists, they got Nobel Prize to actually to violate the Bell inequality in their laboratory. So far in this competition, quantum mechanics is winner. But who knows, in the future, if you talk about the truth, so the reality should be true in whole universe, not just on the Earth. Okay, so keep this in your mind. That was a little bit about the philosophy of entanglement. But the second question, how we could measure entanglement. So there are different ways actually. It depends how you could define your system. So I can tell you, for example, if you consider two atoms which are entangled, or two photons, or atom and photon. So in my thesis, I specifically was working on atom-photon entanglement. And also I was focusing on semi-classical point of view. It means that I considered atom as a quantum object and the photon as a classical object. Of course, the light is a classical object, but in reality, we know that this is not true. This is just an approximation. But when we are talking about laser, actually laser is a coherent state of the light, and it's one of the most similar part of the light that it's behaved classically, and we can use this approximation. Okay, so consider a realistic example, a vapor star of a rubidium atoms, which are alkali atoms and which are in interaction with light, laser field. So because of the interaction of this laser field and these atoms, so some information could be shared. So this atom, you can consider that these atoms, so actually these atoms have some states. And you can model these states, these energy states, in different models. So all of us, because of the chemistry, we know that, so the atoms, actually, there are some orbitals in the atoms, and you can consider some states and some energy states, energy level for you can model your atom in some energy levels. Okay, and so based on the type of the atoms that you are studying, you can consider, for example, lambda type, V type, double lambda, or whatsoever. So I consider some model, and I consider my atom as a quantum object, and the light, the laser light, as a classical object. So the atoms are quantum. I use the statistical quantum mechanics. It means that so these states, you can write a density matrix for your states, and one of the good measurement for entanglement is von Neumann entropy. It means that if you use the von Neumann entropy for your measure, so it's equal to measure the entanglement. But actually it has some condition. First of all, your system should be in the initial state, should be in the pure state. And of course, in this specific case that they consider, so the system actually was at the beginning was in the pure state, and because of the interaction and evolving the atoms, evolving the information between the atoms and the photons, so density metrics also was involved during the time. So von Neumann entropy is a good measure. So first of all, I used the Liouville equation. It is better just to show you the formula because you have no idea about Liouville equation, but I explain for you what's going on about it. So it's about the evolution of the density matrix that can be calculated just based on Hamiltonian. So you write your Hamiltonian for the atom, and you actually write the density matrix also for your atom. But you have to consider that this Hamiltonian is dressed Hamiltonian, and your states also are dressed. It means that they have the information of light itself. And so basically, by using this Hamiltonian and density matrix, and by using the Liouville equation, which is just rho dot equal bracket h minus h rho, so you can actually calculate the evolution of a density matrix. And when you have the elements of your density matrix, you can use the von Neumann entropy, which is just S equal minus rho natural logarithm of rho, and then actually you can trace over the information, the whole information, which is in this actually interaction picture between the atom and photons, and you can trace over the diagonal terms, and you can extract the information. So by using the von Neumann entropy, which is a little bit more specialized, and so you need to do some numerical calculations. So I was using MATLAB and also Mathematica to analyze, and I was actually calculating the entanglement in different situations, like multi-photon resonance condition, beyond multi-photon resonance condition, which is talking about the resonance. So it means that if the light is completely tuned to the states, it means that the transition frequency is equal to the frequency of the laser, or it's not equal. So this multi-photon resonance transition is also is important. So so I was calculating this, and in time evolution of entanglement, steady state of entanglement, and so on. I don't want to talk about it in very detail because it's not a formal presentation. It's just I would like to have it like a casual conversation over this interesting topic. And so, and at the end, yeah, we got some results, and that was specific study of entanglement in different situations. And so yes, entanglement is is a very, very interesting feature, full quantum feature of nature that is actually quite helpful for quantum information processing and making quantum computer, which is commercialized nowadays. We know that IBM and Google also actually made quantum computers. And so yeah, that was my video for today. And thank you very much for listening. Thank you all my teachers to teach me, and hope to see you soon again, and take care.